So now I'd like to look at a geometric series that's infinite and ask the question, if this series was to continue going forever, is it possible to calculate a sum of an endless number of terms? Now probably when I ask that question you think, how could that even remotely be possible to add an infinite number of terms and expect to get a fixed sum or a sum at all? Because you would think as you add more terms the sum would continue to change. So we want to investigate this rather strange question, and hopefully before watching this video you've had a little bit of an opportunity to do some exploration and discovery with this concept. So what I'm going to do is I'm going to look at a number of geometric series with different r values. So in my first one I've got an r value of 2. And what I'm going to look at is the sum after 1, after 2, after 3, and so on terms to see if it might even be possible to have the sum of an infinite number of terms. So the sum of the first term is just the first term, 1. The sum of the first 2 terms would be 3. The sum of the first 3 terms would be 7. And the sum of the first 4 terms would be 15. And we can keep going. I just want to mention that you could enlist the help of your calculator with this. What I've got set up here is a table under the stats feature, and in list 1 I have the position, term 1, term 2, term 3. In list 2 I have the value of the term. So term 1 is 1, term 2 is 2, term 3 is 4 listed. And then what I'm going to do is that in list 3 I'm going to come up with a cumulative sum for the terms. And to get the cumulative sum feature, I'm going to go to second function catalog and go to the C's, and there we have cumulative sum. I'm going to bring it into list 3, and I'm going to do the cumulative sum of list 2. So second function list 2. And then I'm just going to bring this table onto the screen so we can see it better. So what I have in list 3 is what I was calculating over here. I have the sum after 4 terms being 15, the sum after 5 terms being 31, and so on. The sum after 6 terms being 63. And you can see that as the number of terms grows, the sum is continuing to grow. And that's because we are adding on a larger and larger number. So in a case like that, it doesn't seem reasonable that we could be approaching one fixed number, so we say that there's no finite sum. We could also look at these sums in a graphical way. Perhaps we regard these sums as the total distance traveled after a certain number of days. So if you start at 0, after 1 day you're 1 meter away, after 2 days you're 3 meters away, then you're 7 meters away, then 15, and then 31, and then 63, and you can see that every day we keep adding more and more, and so we're not going to approach a given fixed sum. Alright, in our next example we have a geometric series with an r value of -2, and so if we find sums, the sum of the first term is 1, sum of the first 2 terms is -1, sum of the first 3 terms is 3, sum of the first 4 terms -5, and so on. Again, I could use my calculator to come up with those consecutive sums. So from my table I can see the partial sums continuing, sum of 11, sum of -21, and sum of 43. And if I were to think of this situation graphically, I start at 0. My total distance traveled after 1 day is 1 meter forward. After 2 days I'm 1 meter back, 1 meter to the left of the origin. After 3 days I'm 3 meters forward, then I'm 5 meters back, then I'm 11 forward, then I'm -21 back. And as you can see, the bouncing back and forth is getting wider on each side of 0. And so we're not converging to a particular number. The sum is not approaching a given value as the number of terms increases. So again we would say there is no finite sum. In the third example, we have a simple geometric series. We can think of this as a ratio of 1. So the sum of the first term is 1, the sum of 2 terms is 2, the sum of 3 terms is 3, and we keep adding 1 each time, so the sum keeps going up by 1 unit. It's like starting at 0 and going 1 unit, then we're going 1 unit every day, and so we keep adding terms, we keep getting further away, we're not approaching any one fixed value, so there's no finite sum. Now we have a series with an r value of -1. So the sum of the first term is 1, sum of the first 2 terms is 0, first 3 terms is 1, and the sum's going to keep alternating back and forth between 1 and 0. We go 1 unit forward, and then we go 1 unit back, so we're back where we started. Forward and back, forward and back. Are we narrowing in on one fixed value? No, we're not. We're alternating back and forth. So this is not approaching one fixed value. So again, we say no finite sum. Now we have a geometric series in which the ratio is a half. And if we work our sums out, let's just do a few of them manually. The sum of the first term is 8. Sum of the first 2 terms is 12. Sum of the first 3 terms is 14. And if I enlist the help of my calculator to get other sums up to a certain point, we can see we have a sum of 15, sum of 15.5, and so on. Now it seems as though we're getting closer and closer here to a particular value. Perhaps 16. Let's see. So we start at 0. We go forward 8. Our total after 2 is 12. Then it's 14. Then it's 15. Then it's 15 and a bit. 15.75. So we're narrowing in on something in this area. Perhaps 16. So we'll predict that if the number of terms was to increase, the sum of the series would get really close to 16. Finally, we have an r value of -1/2. And sums. 8. Sum of the first 2 terms, 4. Sum of the first 3 terms, 6. Sum of the first 4 terms, 5. Sum of the first 5 terms, 5.5. My calculator gives me the sum for more terms, 5.25, 5.375. It looks like we're approaching something in the neighborhood possibly of approximately 5.3. If we look at it visually, our sum is 8, then our sum is 4, then our sum is 6, then our sum is 5, then it's 5.5, then it's 5.25, and it seems like we're narrowing in on something in this range. So again, we predict 5.3. So we've looked at 6 series with different types of r values. When r was 2, we did not have a finite sum of the infinite geometric series. When r was -2, we did not have a finite sum. When r was 1, we did not have a finite sum. When r was -1, we did not have a finite sum. When r was 1/2, we did have a finite sum, and we were estimating that to be 16. And when r was -1/2, we did have a finite sum. We estimated that, but we're not sure to be 5.3-ish. The question is, when is there a finite sum to an infinite geometric series, and when isn't there? Well, in these two cases, what's different than the above is the fact that the terms are all approaching 0 as the number of terms increases. The terms are all going towards 0. And if you ask yourself what's causing the terms to go towards 0, it's the fact that we're multiplying by an r value that's less than 1 or greater than -1. And the value of the terms approaching 0 is significant for there being a sum or not, because it means that as the number of terms grows, those terms approach 0, and so it's as if you're adding less and less, and almost an insignificant amount after a while, because the terms are so small. So there will be an infinite sum for a geometric series if the terms approach 0, which means the ratio is between -1 and 1 for the geometric series. The question now is exactly how do we calculate this via a formula? To answer that, let's look back to our understanding of a finite geometric series. We have two formulas for calculating the sum of a finite geometric series, from term 1 up to term n. Now we can extend this to an infinite series by continuing on by multiplying by r. So that would be t1 r to the n, which is the same thing as tn times r, and so on. And so if we look at each of these terms approaching 0, we can say these terms eventually get so small that they're almost 0. So in our finite formula, if we were to put 0 into this part here, which represents the nth term times r, that should give us the sum of an infinite number of terms for a geometric series. So we're going to pretend that this is 0. It's so small that it's insignificant, so that's going to leave us with negative t1 over r minus 1. And if we just multiply top and bottom of that by negative 1, that would mean that the sum of an infinite series is t1 over 1 minus r. And we get a finite sum, remember, as long as the ratio is between 1 and negative 1. So let's see how this formula works with the two series we've been looking at in this video. If our ratio is a half, there will be a finite sum. And we can get that finite sum from this formula. Term 1 is 8. And so if I put the numbers into the formula, 8 over 1 minus a half, which is 8 over a half, and 8 divided by a half is 8 times 2, which is a sum of 16. Let's use the formula with this second example as well. Term 1 is 8, r is negative a half. We suspect that the sum is around 5.3. The formula will give us that sum precisely. So we have 1 minus negative a half, which is 3 halves, and 8 times 2/3 would be 16/3, which is 5.3. Repeating would be the sum of the infinite series.